Okay, good morning, everyone. So tomorrow we will be having a quiz number 3, which will cover the which will cover the content of the previous week. So I will make an announcement today, and it's the logistics will be similar to the logistics of the previous quiz. So it will be a grade scope. It will be organized with a grade scope, and again, you will have a 90-minute window starting from 11 a.m. On Thursday to 11 p.m. To 11 a.m. on Friday to submit the quiz. Right, and then on Friday we'll have a discussion about this week problems. So all follow-on quizzes will be on Thursdays, except on next week on week 5 when we'll have a midterm. It will last for 2 hours, like 2.5 hours. But yeah, the format of the midterm will be similar, and the midterm will cover the materials of the first 4 weeks. Any questions? Any questions about logistics, about homework? Okay. And are midterm questions the same level? Yes, the level of difficulty will be more or less consistent throughout all the tests. I might give again some bonus problems for fun. Yeah, so the test results are, so the midterm will be next Thursday, correct? So all tests on Thursdays, well, except the finals. The final will be on the last day. We'll announce that separately, and then all discussions on Fridays. Will the midterm have extra credit problems? Possibly, yes. I haven't built it yet, but possibly. Yeah, so the results of the quiz are out, I think, right? So I believe there was some mishap in counting the percentage, but now I think the TA has fixed that. So we have 2 TAs, Emma and Ruben, so they would grade tests in alteration. So next test will be graded by Emma again. Sure. Okay, so last time we talked about partial derivatives and chain rule, and so here's the formula. So so let me remind you, a partial derivative is a derivative of a function which has a if we have a function with many variables, right? So we could fix all other variables except one, right? And then we would calculate the partial derivative as a derivative of the function with respect to the remaining variable, right? So therefore, if you have n variables, we have n different partial derivatives. We can say it in all directions. Like if you have f of x1 through xn, we can take derivatives over any of those variables. And we also talked about differentiability and differentials last time. So the function is differentiable, right? If the differential exists, right? So that the change of the function in with respect to the change of the, so here, right? So change of the function with respect to change of the arguments becomes the differential of the function in the limit when the delta x and delta y go to 0. So in other words, the remainder here, this function phi, should go to 0 faster than delta x or delta y. So you can say here that limit of this phi divided by the distance from point x0, y0 to point xy goes to 0. So if you think in terms of a Taylor formula, if all derivatives exist, right, then the this phi is literally will be the first remainder R1 for the Taylor series, and for the construction, it does satisfy this quality. Sometimes, though, the function is not differentiable, starting from some number, from some value, and then that's the best you can get. Okay. So I've been advertising complex variables here throughout the course, so let me give you one more advertisement. So here we say, well, okay, so then so there is of course a one-to-one correspondence, as we discussed, between two-dimensional functions, real functions of two variables, and a complex function. Well, I mean, yeah. So in a sense, if you replace, write it here, like in a bracket. So if you say that z, well, it's a different z than the function, but if you say that z is equal to x plus iy, and then you can consider function f of xy, you can represent it as a single function, what's called g. So not to abuse the notation of single complex variable z, right? And then you can study differentiability. So if the function g is differentiable in a complex sense, right, and in this case, the word holomorphic is used, right? So holomorphic means complex differentiables. Essentially, it's a similar formula, only now instead of the delta x and delta y, you write it as a delta z in a complex sense. So the delta x and delta y, like these two terms are not completely independent as here, because you would want to write it as, g prime of z0, right, times delta z. And let's call it delta, big delta f. Yeah. So delta f would look like, well, delta g, excuse me. G is sort of f. Yeah, so delta g like this plus some function phi of z, which obeys the same properties. So it would go to 0 faster than delta z. So if this happens in a complex function, so in other words, if this function is differentiable at some point, meaning that this equality is true in a disk, in a small disk centered at point 0, then you get that function is also differentiable twice, thrice, 4 times, and infinitely many times. So for complex function, complex differentiability is a very powerful statement. So if a function is holomorphic or complex differentiable, it means that it's differentiable infinitely many times, and you can write a Taylor series for the function, which will converge inside some disk of convergence. So the calculation of convergence, like the radius of convergence, is done analogously to functions of to a series of power series in real variables. But yeah, so the key distinction here is that the complex differentiability is really a very powerful statement, right? So you can express it in terms of what it means in terms of fx and fy. There will be some conditions with constraints, which are called Cauchy-Riemann equations, that relate derivatives of real part and imaginary part relative to x and y. Yeah. So anyway, so it was an advertisement for the 185 class. So I highly recommend to take it. I believe it's in. I mean, you cannot not take it in a sense, but so it's one of my favorite classes to teach. Anyhow, so we talked about a bunch of examples, and then we discussed the differentials, and we talked about chain rule. Right. So the way chain rule works, you simply apply it for every function, right? So you look if you have a function of parameters. Let me go to the second example right away. So So you have, if you have a parameter t inside the function f, then if you calculate the differential, you just collect all derivatives in all terms, right, and add them together like this. Okay. Any questions? Okay. Yeah, here's the formula for the partial derivatives of the function if you have several parameters. In fact, the number of parameters is independent on the number of variables. There can be as many as you want. Yeah. Okay. So one more story about this differentiation is implicit differentiation. So when it appears when the function is not given by an explicit formula, right? So instead of having z equals f of x and y, or y is equal to f of x, we're given an equation, say being f of x comma y is equal to 0, right? And often it's not possible to rewrite it as explicitly as y equals to f of x, as we know, for example, in the case of parametric curves. So we should work with this implicit formula. And yeah, so for us, it's no stranger because, well, we know how to deal with parametric equations. But now, let's say I want to find the derivative of, so our goal is to calculate derivative of y with respect to x, given the fact that they are subject to this constraint. Okay, but using the above formula, we can actually do that quite quickly. So let's differentiate both parts of this equation by x, right? So if you do d over dx over dx of f of xy is also equals to 0, or using the chain rule, it gives us df over dx. Now then we're looking at the first argument here, times dx over dx. Right, so it appears in argument, so we should use that. So of course, dx over dx is equal to 1. And then the second term looks like dx over dy, dy over dx. And that's equal to 0. So this becomes 1, and we can find dy over dx from here. Which is minus d capital F over dx divided by df over dy. So in the denominator, when we calculate the derivative, it is assumed that the y is a variable, right? So it does not, we ignore its dependence on x. Just, oh. Okay. Okay, so that's example of a function of one variable. So let's give an example. Say f of xy is equal to x to the 6th plus x to the 5th plus 7xy. And so you don't want to solve y. You don't want to solve it explicitly as y as a function of x, but using this formula, we can easily do that. Right? So dy over. Actually, I think I made a typo. So y is a single function of x. The function of x is a single variable, so there should be a straight derivative. Like it's just an ordinary function of one variable. Or you can write it as y prime. Yes. So y prime is equal to, I'm looking at the formula, negative yes, df over dx over df over dy. That gives us 5x to the 4 plus 7 7y with a minus sign and divided by 6y to the 5 plus 7x. Right, so that's it. That's the implicit derivative. Well, so that's the implicit differentiation of a function y of x, which is given implicitly as the equation f of x y equals to 0. Questions? And finally, well, let's so that gives you this equation describes implicitly a function of one variable. Now let's do the function of two variables or many variables in that sense. So now let's assume that we have, so we want to define, say there's a function z of xy given implicitly by equation f of x comma y comma z, which is f of xy is equal to 0. So, and that happens in some domain. X and y, they belong to a certain domain of this function. So our goal is to calculate partial derivatives of f and y of f. It's f prime x and f prime y. Right. So let's apply derivatives of function. Let's compute d over dx of f of xy f of xy. And so we know how to do that. It's df over dx times dx over dx plus df over dy times dx or dy over dx. Well, I just do it once but for completeness, and then we're not going to do it again anymore. So now df over dz, right? So say this is the third position here is reserved for letter z. For the third variable z, is just we treat it as z is a function of x and y. So df over dz when multiplied by the little f, the partial derivative over dx. And that is equal to 0. Is use of capital F to indicate the antiderivative? No, it is not. So it's just a different function. So often in mathematics we use the same letter to denote functions which appear in a similar context, but we use different fonts. Well, there's no at all relationship with antiderivative. To begin with, it's a function of several variables. Right? Okay, now dx over dx is equal to 1. dy over dx is equal to remember, x and y are independent variables, right? So they just live in some domain of the plane. What happens if you differentiate independent variable over another independent variable? So, what do you think dy over dx is equal to? So y does not depend on x. Yeah, that's right. So often, if the question is asked in this way, the answer is 0. Is that clear? So x and y are independent variables, and then you can still formally treat y as a function of x, but that's a function that is not really. It's a constant function. Yeah, so these variables are independent, so it goes to 0. And that brings us to df over dx plus df over dz partial f over partial x. From here, we can just solve it for this f prime, which is given by minus df over dx divided by df over dz. So that's the x component. Now, let's do the y component similarly. So here we can do a bit quicker. So it's well, but anyhow, so let's do it. So it's df over dx, dx over dy, and this of course will be 0 because of the same reason, plus df over dy times dy over dy, which is equal to 1, and then plus df over dz f prime y, which leads us to a similar formula. And of course, you see how to generalize it to other to the functions of many variables. Okay. Let's do another example. So, so there's a function f of x, y, and z, which is given by x, y, z, plus x squared plus y squared plus z squared minus 4. This is so-called, it has nothing to do with the course, but anyhow, it's called Markov Cubic. And it's used quite a lot in algebraic geometry. In fact, I'm using one of this in one of my papers. Anyhow, so let's calculate derivative. So assume that z, so yeah, so z, it gives f of xy, right? And let's calculate this z f prime of x and f prime of y. Okay. And let's maybe evaluate those derivatives at x, y. Okay, let's do it. Let's just write it down. So f prime of x is equal to, I'm just using the formula in the train formula over there, so it's minus df over dx. So it's yz plus 2x over df over dz. Xy plus 2z, right? And f prime of y is equal to negative xz plus y divided by xy plus 2z. These are rational functions like that. Questions? Okay. Great. So our next story today will be about gradients, directional derivatives and gradients. We'll go to its subsection 14.6. So now when we have functions of many variables, and then chapter 14 won't be on the quiz. Well, it won't, correct. It will not be on this quiz tomorrow. It will appear partly on the final, on the midterm next Thursday. Okay. Right. So now, well, we have defined partial derivatives as well. Let's recall the definition. So f prime x at point x0, y0 was equal to, we took the limit of the function as, yes, of x and y goes to x0, y0. Then there's a f of, we shift the, we only shift the x variable, and we keep the y variable constant, right? So actually, yeah, I should have written h goes to 0. So yeah, that's right. So h goes to 0 divided by h. That's 1, and then similarly, there's a derivative f prime y, where you do the same, and then you shift the y variable. But now, why, you can ask, why do we always do this shifts in x and y? Why cannot we go at a 45-degree angle or a 30-degree angle? Well, of course we can. And that brings us to the notion of the directional derivative. And so, say you have your, well, the function is given, there's some surface here, which is the graph of the function. Z equals to f of xy, right? And then you're sitting at some point x0, y0, f of x0, y0. on the surface, and well, you're doing this. Say these are the vectors which are parallel to x and y axes. So we have f prime x goes this way, f prime y go that way, and we discussed what this means, right? We have, they show us the how the function behaves in those slices, right? So if you slice our surface by respective planes, then in the cross section we'll have a curve, which will be the graph of the function at constant values of y and x respectively, and that's what these derivatives do. Right? But now, well, why not just do, can't we just go like this, right? So sort of pick a vector in some direction, right? So vector u. It can be of the unit length, just for convenience, right? Say, it's a vector that makes, 37 degrees, right? With the x-axis. And can we calculate the derivative there, right? So we want to understand how the function behaves as we change, as we dissect the graph, the surface by the plane that's oriented in this way, right? So this plane would contain vector u, and also vector, and also it will be parallel to the z-axis. Excuse me, it will also contain the z-axis, right? So so you would dissect it with a plane, which would go like this, right? So it would cut through u and z, and then in a cross section, just don't want to contaminate the picture. In a cross section, we have some curve that goes like that. So to which vector u will be tangent? Why 37 degrees? Why not? Pick your favorite angle. So in fact, in a minute we'll study all possible angles, right? So so we need to have a tool to be able to go anywhere on the curve. Right? So here's the definition. The directional derivative of function f at x0 y0 in the direction u, which is given by components a and b, right, is the following thing. It's let's call it big D with subscript u, f of x0 y0, or you can also write it as just du, del u, that's fine too. Usually in differential geometry, capital D is referred, reserved to something else, the so-called covariant derivative. It's not what we're talking about here. And it's given by, well, the limit. So again, there's a parameter h that goes to 0, and now we do f of x0 plus h times a. Right, so a is the x component of the vector, y0 plus h times b minus f of x0 y0 over h. Right, so the picture that we just drew it illustrates this definition. So if your angle is indeed 37 degrees, then a is equal to cosine of 37 degrees and b is equal to sine of 37 degrees. Yeah. So this way you can define the derivative in any direction. Okay. Any questions? Okay, now we need some tools to calculate that. So it may not be convenient to just always take this limit. Instead, we should have some, rather easy formula to calculate this derivative. And this is what we can do. So it says that if function f is differentiable at x0, y0, meaning that that formula with differences exists in some small disk, right? Then directional derivative exists in direction of any unit vector. That exists for any unit vector u with components a and b, and the following formula is true, so that df over du x0, y0 is equal to just the linear combination f prime x, x0, x0 times a plus f prime y, fx0, y0 times b. Okay. Now, yes, so it's important for this formula to work that u is the unit vector, right? So absolute value of u is equal to 1. I mean, the analog of the formula would work for any vector u, but there will be some scalar multiple in front. Okay, let's prove it. So basically, it's very intuitive. You just take linear combination of this partial derivative. So when you can check here that the formula kind of passes all the sanity checks. So if your directional derivative goes along the x-axis, then a is equal to 1 and b is equal to 0. So you get df over du is equal to f prime x. Okay. So for short, let's define a function g of h, which is f of x0 plus h times a, y0 plus h times b, right? And then what we need to do, we need to evaluate its derivative at h equals to 0. And so then this du f of x0, y0, right, by construction is equal to, well, I'm not going to copy the formula from the top, but if you look at the formula here, that's exactly you'll get, it's the same as limit as h goes to 0, g of h minus g of 0 divided by h, which is g prime of 0. And so if you put h equals to 0 here, you'll get f of x0, y0. And now let's apply the chain rule So we need to evaluate this derivative and then put it at h equal to 0. Let's first calculate it. So g prime, right? So g prime of h, there's only it's a function of one variable, is equal to df over dx. So by x we just denote the first argument. This is x, this is y, times dx over dh plus df over dy h times dy over dh right, and that gives us yeah, so it's f prime x times a plus f prime y times b, right? Yeah, and then of course derivative g prime of 0 is f prime of x, that's x0 y0 times a plus f prime y x0 y0 times b. Yeah. So in terms of the angle theta, a you can write it as a cosine theta and b is equal to sine theta, where theta is just a polar angle in the local coordinate system. So let's do a quick example. Let's take our Markov cubic again. Can we just do it over there? There's enough spot. Yeah. So here's the Markov cubic, and let's calculate the directional derivative. Let's say pick a vector. The direction of theta is equal to pi over 6. Right? So it's a derivative, directional derivative in the direction which makes 30 degrees with the x-axis. And so we have, and then say, let's calculate it at x equals y is equal to 0. Can we do that? Shall I give it a try? Well, remember, I'll write the formula and then I'll do it. So the du of f, right? So here u has components cosine pi over 6, which is root 3 over 2, and sine pi over 6, which is 1/2, and df over du is equal to f prime x a plus f prime y b. So these are a and b. So can we evaluate that? What will be at x equals y equals 0? The answer is probably it's not so yeah. The answer will be trivial, right? At 0. Yeah, so first, let's do it at 2 points. So first, x, y is equal to 0, 0. And second, at xy is equal to 2, 0. So remember that this, although the formulae contain a z explicitly, right? We can use the equation to find z. So what will be the answer for b? So if x and y is equal to 0, what is the value of z? Yeah, that's right. So, oh no, is it the answer for the value of z or the answer for the directional derivative? So remember, there's a 4 here. So if x and y vanish, then this is 0, this is 0. So z is equal to 2 or minus 2, right? There's a there are 2 points, plus and minus 2. So let's say we pick plus 2, right? And then we get, so now we need to take the limit. So z is equal to, well, the plus and minus 2, but when x and y equal to 0, the numerator of both functions, of both ratios is 0, right? So this is 0, this is 0. So therefore, it just, here the linear combination is trivial, it's equal to 0. But now it's slightly less, slightly more non-trivial. Example one, x and y is equal to 2, and say x is equal to 2, y is equal to 0. Right, so in this case, this is still 0 because of the 1, 0. And then say, yeah, so we have 4 plus 0 plus z minus 4 equals 0. So z is equal to 0. Okay, so can we find the derivative now? I guess it's getting here is getting becoming infinity, right? Sort of the, do you see it, right? So in this case the z approaches, so z is 0, and then x is equal to, so the denominator is equal to 0 in both fractions, and the numerator is not equal to 0, right? So in this, in second case, the derivative is equal to infinity. But so for any other value, it will be some linear combination of these two vectors. Okay. Questions? Finding the derivative of both. Yeah. So we found them both, and then we plugging them into this formula. Yeah. Sure. So we have this. We did this calculation 10 minutes ago. Yes, that's why we can use it. So we have found it. So what do the 1x, y, and 2x represent again? Oh, it just I asked you to do the calculation at 2 different points, right? So think of it. So this gives you some surface, right? This equation gives you some surface in 3 dimensions, and I'm asking to calculate the directional derivative at point 0, 0, first in the direction of vector u, and second at point 2, 2, 0 in the direction of vector u. So the general recipe works like this, right? So if f prime and x prime are given by these expressions, then the directional derivative at any point xy is given by this formula. Okay, good. Okay, let's make a quick break. Let's reconvene after 7 minutes. Okay. Right. Now, so let's see what, right, so we talked about directional derivative, which in this case is a scalar, right? It's a function. But now we want to create a vector function, vector valued function, which sort of has the knowledge about direction in which the derivative we take. And this brings us to the notion of the gradient vector. So by looking at the formula above, right, so this g prime, the directional derivative, we can see that in fact du of f, we can represent it as a dot product of vector with components f prime x, f prime y times, just put down this, times ab. Okay, so indeed, if you take the dot product, then that will be exactly what we have. Okay. Now, and this vector here is called the gradient vector, and it's denoted with the symbol nabla. Yeah, and the symbol is pronounced as nabla. Nabla. Well, let's write it as a formal definition because it's kind of important. So let f of x, y have partial derivatives f prime x and f prime y, then the gradient of f is the following vector function, which is denoted nabla f. You can put a vector here, and this is the vector with components fx, fy, or you can write it in terms of basis vectors. Fx times I plus f prime x j. And so this way it encodes, like if you dot it with the directional vector, you will calculate the direction of the derivatives. Now du f, the directional derivative, is therefore dot product of the gradient vector with the directional vector. Oops. Okay. So we can, yes, we can calculate it for any example. Okay, maybe we'll just do one calculation. Let's take f of x, y to be equal to square root of 1 minus x squared minus y squared. It's a northern hemisphere, right, of a sphere of radius 1. So then its derivatives f prime is equal to minus x over root 1 minus x squared minus y squared. f prime x, and then f prime y is equal to minus y. Like this. Don't worry about the sound, it's the, it will go away. Yeah, so this is the gradient vector. Here it has the same coefficient, right? It's 1 over the square root. With components minus x minus y. Right, so it's yes. So if you are at a point xy, and then you live on a sphere on this hemisphere, this is the it's the vector that points points back at the origin, right? So the let me try to draw it. Let's say this is the hemisphere, right? And then the coordinate system, and say we're here at point xy, right? So this is the value of f of xy. So the gradient vector here would point towards the center, right? So towards the origin. So here it would go like this. So yeah, it will always be a vector which is aligned to with the origin and the point xy. So right, kind of in a sense, it goes in the well. We'll talk in a second what it means, but sort of so as well as you know, as you sort of slide from this hill, right, you would if you put a point right on this hemisphere and you would let it go, right, then the gradient always points towards it. Not necessarily. In this case, it does, but we'll talk in a second about where it points. Yeah. So in this case, it does, but here it's mostly because of the symmetry, right? Because the shape is rotationally symmetric. Good. So now let's talk more about the direction. Then the what does the direction of the gradient mean? Okay, so let's do it here. So here's the theorem. Is that so suppose f is a differentiable function of two variables. Okay, and then the maximum value of the directional derivative is equal to the absolute value of the gradient. Maximum value of this directional derivative del u f is equal to absolute value of nabla f. And it occurs when vector u has the same direction as the gradient. When vector u is parallel to the gradient. So the meaning of the gradient vector, it shows, so if the directional derivative takes its maximal value, means that the function changes in that direction the most, right? So it's like the direction of the most rapid change of the value of the function. So therefore, gradient shows us where the function change, sort of where this, in which direction this thing happens. Okay, so let's prove the theorem, and then we'll look at examples. And then, of course, here it's we give an example for two variables, but of course you can generalize it to any number of variables, right? So all the formula will go one-to-one. So the directional derivative del u f, as we know, it's the scalar product, the dot product of u with the gradient. And then, of course, we know what what the dot product is, right? We just take absolute value of f times absolute value of u, which is 1 in this case, times cosine of the angle between them. So since u is unit vector, cosine theta, and the theorem follows immediately from here, right? So this function can be maximized if theta is equal to 0, right? So right, so therefore the vector, the gradient vector has to go along the directional vector. Yeah, so when so the direction in which the directional derivative is maximal corresponds to the direction of the gradient. Okay. Okay, good. So let's look at an example and then we'll do some plots. So let's say you have f of x y is equal to x times e to the y. So and then let's say we fix a point P with coordinates 2, 0. And then we need to find the gradient of this function in that point. Right, so let's calculate the gradient. It looks like, so it's the vector with components f prime x, f prime y, which is e to the y times x e to the y. Right, and then the value of the gradient at point at 2, 0 is equal to 1, 2, and so exponential is equal to 0. Right. Now the yeah. So the well, to see how this works, let's plot this function. Right, so right, so it looks like this. And, right, and then the so we have found here that the maybe let's do it from 0. See the direction of the growth. 0 to 2, 0 to 2. And so due to the exponential in y direction, the function grows. Well, so basically the function grows exponentially in y direction, and it grows linearly in x direction. So it goes like that, and then the point with coordinates, so point P here, has coordinates 2, 0. Maybe let's do 2, 3. Right, so point P is here. Right, and the component of the gradient that we have found were, so nabla f at point P at 2, 0 had components 1 and 2, right? So it's a vector that goes like that. And you can see from the plot, right? So that it exactly shows where the hill is steepest, right? So where it climbs the fastest. So any other direction, right? If you go along any other direction, you're not going to climb as fast. So the function will not change as fast. What did you write the first coordinate for nabla f? Oh, it's 1. 2. I'm sorry. Yeah, excuse me. Sometimes it's tricky to draw on this annotation thing. It's 2, 0. So this is the point P has coordinates 2, 0. And so we're calculating the gradient at that point. So it's the same. I'm just going to show the plot. Yeah. And that's so here you also see why in the example with the hemisphere, the gradient vector was directed towards the origin, right? It's because let's do it here. Any questions on this plot? I wanted to switch to that thing. So yeah, so gradient shows the direction of the maximal change of the function, right? So it maximizes the directional derivative. So let's do the 1 minus x squared minus 1 is y squared. Switch to limits here. Right, and then, well, obviously, if you want to go, climb the mountain, right? So the hardest way to do it would be through, if you go up, right? So at any point here, the gradient should go this way, right? Like this direction. So at this point, it will be in that direction. The maximal so direction is in which the function changes the most. This gradient direction, in this case, is towards the origin. So yeah, good. Any questions? Of course, if you change something like this, put some, for your a here, let's say a is equal to 1.5 or whatever, like then it gets stretched a little, right? And then in this case, the direction would change, right? So like the direction, yeah. So you will calculate the derivative, right? And it will contain this vector, the coefficient 3, and it would change the direction of the maximal growth of the function. Okay. Let's maybe do one more example with a function of 3 variables. So say you have a function f of x, y, and z, which is equal to 80 divided by 1 plus x squared plus 2y squared plus 3z squared. And then this function was taken from some model of the temperature in some environment, right? So it's basically it's a function of temperature as you change the basically you have some source of heat in the room, say. So when x equals y equals to 0, the temperature is equal to 80 degrees, and then as you move away in different directions, the temperature drops. In particular, well, it can drop. Here it shows that it drops faster if you go in z direction, so it drops faster if you go up, then horizontally, and somehow in y direction drops faster than the x direction. There's some asymmetry here. So let's figure out in which direction does the temperature increase fastest at the point P1, 1, minus 2. So in which direction, essentially, what is the gradient direction? In which direction does the temperature change the most? Yes, that's 80. So then you are measuring temperature in Fahrenheit. Okay, so let's calculate the gradient. Now it's a three-dimensional function. It's a function of 3 variables. It's a vector with coordinates f prime x, f prime y, f prime z. And so derivative of x will be what? 100. Let's take 80 out of the vector. It's a common factor. So here we have 2x with a minus sign over 1 plus x squared plus 2y squared plus 3z squared, everything squared. And the y component will be 4y divided by the same denominator squared. And then here we have 6z minus divided by the same thing squared. So we can single out we can write minus 80 divided by the denominator 1 plus x squared plus 2 y squared plus 3 z squared, everything squared. And here we have, we can even take out 160. Here we have x, 2, y, and 3z. Right, and then now if you plug in here x equals 1, right, so we evaluated at p. So x equals 1, y equals 1, and z equals -2. And so that will give us negative 160 divided by 1 plus 1 plus 2 plus 3 times 4, right? So plus 12, everything squared, multiplied by 1, 2, and 6, minus 6. So here we have, in a denominator, it's 16 squared, which is 256. So the vector is equal to negative 160 over 256, 1, 2, minus 6. Or, well, we can divide by 32, right? So this way going to be 5/8 minus 5/8, 1, 2, minus 6. So if it's a gradient, right, then the temperature changes the most in the fastest way in the direction of this vector, right? And then we can also calculate the absolute value. Right, so it's 5/8 times square root of 1 plus 4 plus 36, which is 5/8 times square root of 41. So if you want to draw it, right, so this vector will have, well, so it's, well, let's write it like this. It's 5/8 minus 1 minus 2 and 6, right? So it goes down and excuse me, it goes towards the origin and up, right? So x component is negative, y component is negative. So yes, it goes towards the origin and then it goes up at the slope whose tangent is equal to 6. And so Daniel, is your question resolved? Okay, great. So right, so that's the story about the gradient. It's something. It's a very intuitive tool. So sometimes when you want to study, so gradients are used in many applications. Like so, say you have a function of many variables, and you need to know, like, well, where basically you need to find all the values, right? Like where in which direction the function changes most. You just take gradients, and then you can use those gradient trajectories, right? So say you have, let me give you an example. Say you have a sphere, which it's not really a sphere, it looks like a heart, right? It's, you know, these are kind of two kind of lobes of the, basically you took a sphere and then you deformed it like that. like this. And then, well, you can start from the top here, and then you can ask, how will you roll down, right? So you only live on a sphere, and say on this surface, it's topologically a sphere. Of course, it's not a sphere. And then you roll down. So of course, like you will fall down along the direction of the gradient, right? So where the sort of the gravity will take you along the fastest path. So you would go here. You would move down to this valley, right? And then you can probably bounce up and down. And once since it's not a stable point, you will eventually fall, right? And you would fall, for example, along this trajectory like this. And you would fall all the way down to the bottom. So in physics, some of you probably know, right, so that if you have if v of x, right, is the scalar potential, so say it's a potential of a gravitational force or potential of the electric force. Right, then the force is equal to negative, there's a minus sign, which is in sense a convention, gradient of the potential. And so let me show you an example. If you haven't seen this before, so we take a gravity force. Well, in space, right? So we have the two masses. Say you have mass big M and mass M, right? So we can again come back to the Kepler laws. So the formula that we had for the force was equal to G Newton M times little m divided by r squared, and then the minus sign in the direction r over r, right? So let's call it u. So u was the unit vector in the direction of the smaller mass, right? And then the force, it was an attractive force, right? So the minus appears in attractive forces. Well, now, can you find the function v, although yeah, I'll have to say, yeah, so now let's take a function v of r. So say it only depends on r, right? So what was the definition of scalar potential again? It measures the potential energy, right? So good. So here's, so say you want to find the potential energy. I didn't give the definition, right? So, but I wanted to illustrate this equation. But okay, so since you asked, so potential energy of this little mass m in the field of gravity of the big mass will be equal to v at that point, right? So at this, if you can draw a radius vector r, right? It will be v of r times m. So I'm about to write the formula for the potential. So potential here, it will be G Newton m divided by minus G Newton m divided by r. So if you want to find the potential energy, but you would need to multiply it by the mass, right? And then we can check that that this formula works. So I'm doing so we'll talk about this next week. I think I forgot what's the next topic in the course, but anyhow, when you live in 3 dimensions, you can use so in 2 dimensions there we have polar coordinates. In 3 dimensions we have spherical coordinates, right? So instead of you looking at the point of the surface of a sphere, and then it has a distance from origin, and now it's characterized by 2 angles, right? So theta and phi. But since we know that the motion is planar, we can just take the gradient. We can calculate the gradient in the as if this happens in one plane, right? So and then we can check that the derivative dv over dr, right, is equal to the well, minus g Newton mm over r squared, right? That's actually no, we don't need the minus sign, right? So that no, wait, sorry, we need minus. Everything's right. So that's dv over dr, and then dv over d theta is equal to 0, right? So the formula does not depend on the polar angle when the point moves. Okay. And now, well, there's a formula for the gradient in polar coordinates. You can actually, well, we'll derive it later. But if you use that formula, you'll get, if you use this formula for the gradient, you'll get the formula for the force. Right, so there's an extra minus here. Hold on, I think I left, there's a plus, sorry. Minus here, then another minus comes from the derivative because it's 1 over r, and then yeah, if you do it in the gradient way, right? So then you get the force, which is negative g Newton mm over r squared times u. Yeah. So gradient of the potential up to a sign gives you the force. So if you take this function, take a derivative with respect to r. What's the derivative of 1 over r? It's negative 1 over r squared. Yeah. Okay. Good. Yeah, we'll talk a little bit more about this computations a bit later. Great. And then one more story for today will be about level surfaces and tangent planes to level surfaces. So consider a function of 3 variables, f of x, y, and z. Say w is equal to f of x, y, and z. Now, the would-to-be graph of this function would contain 4 variables, right? So it's x, y, z, and w. So we cannot plot it in 3 dimensions. But what we can plot, we can do the we can plot level surfaces, and so in other words, we can plot a surface in 3 dimensions, which says that this thing is a constant, right? So in other words, we can take a 3-dimensional space, right? And then at every value of that constant, we'll get a surface. This surface, like one surface, one value of constant, there's another surface on top of it with another value of constant, and then maybe some small surface for another value of constant, right? So here, let's call it constant k. And then here, an example, we have, K1 for red, K2 for purple, and K3 for orange. Yeah. So so now we want to we can parameterize the surfaces in terms of a vector function, right? And let's say there's a we can have, right, so let's say we fix a surface. Let's call it S, right? So it's one of those three or any others. And then there's a curve on the surface. Call it C. And the curve, as we know, is parameterized by a vector function. So let's say there's a function R of t, which is given by x of t y of t, z of t. So it would look like, say there's a curve on the on one of those things. Say there's a curve that comes back here. So it's a curve C that, yes, so it's, which lies on S. And this surface S is given by the equation F. So, and S is provided by equation F of x, y, z is equal to K. Right. So there is a surface, which is a level surface of the function of three variables, and then there's a curve that lies on that surface. Now, because this curve lies on the surface, if the curve C is described by the vector function R, we can also write that f of x of t, y of t, z of t is equal to K. So that's yet another way to parameterize the curve C. And now let's find the tangent plane, right? Let's find a tangent plane to this level surface. So our goal is to find the equation for some plane that would touch the level surface at a point say somewhere here, at the point of R0, so that it would, so we need to find the derivatives, the tangent, the partial derivatives, which lie in the, so in order to find the tangent plane, we need to find two vectors, right, that parameterize this plane. Okay, and then the way we're going to do it is that we'll first we'll calculate the gradient of f. So in three dimensions, right? So gradient of f will show us in which direction the those layers, those surface layers grow the fastest, right? So gradient, and then that would show us, that will give us a vector which is perpendicular to this, perpendicular to that plane, right? So gradient f, because we're looking for the tangent plane, right? And the tangent plane will be orthogonal. So, and then the gradient of f will play the role of the normal vector. So the idea will be that the plane will be given by this equation, right? So the nabla f time dot with the derivative is equal to 0, right? So, or maybe let's erase one of those vectors. So the if say the first vector here is the derivative vector, so it's well that's the right. I'm gonna write it here. So it's, we have r prime of t is the tangent vector to the curve. Tangent vector to the curve C, right? That belongs on the surface S, and nabla f, the gradient is the normal vector. So as we learned 2 weeks ago, in order to describe a plane, it suffices to write this equation, right? It's a condition that the normal vector is orthogonal to any vector that lies in the plane. In this case, it will be a tangent vector to some curve. Now, keep in mind that which curve, it doesn't really matter. You can pick your favorite curve on the surface and study its tangent vector. So, and then we also need to know the point where it's anchored, right? So say we have a point R0 with coordinates x0, y0, z0. And then therefore, when t is equal to t0, we have x equals x0, y equals y0, and z equals z0. Right, so therefore, we can write the following equation that so that we have r prime, right, will have components r prime of t0 will have components x minus x0, y minus y0, and z minus z0 for some point x on the plane. And the gradient has the usual components, right? So therefore, this equation can be written like this. So it's f prime of x times x minus x0 plus f prime of y, y minus y0 plus f prime of z, z minus z0 is equal to 0. Okay. So that would be, yeah, so that's the equation of the plane that is tangent to the surface, to the level surface of the function of the variable. You're probably out of time today, but we'll start with an example tomorrow, and then I can answer your questions about the quiz. Oh yeah, and also today we have office hours, right? So the office hours at 2 as usual. I can send a reminder. Quiz will cover section 13. Yeah, yes. Other questions? Okay, so if not, then thanks for joining, and I'll see you tomorrow. Thanks, bye.